You know, people think they understand glass. You look through a window, light goes through, seems perfectly reasonable. But if you actually stop and think about what's happening, really happening at the level of atoms and electrons, glass becomes one of the most bizarre things in the universe. And I mean that seriously. It's so weird that most people, even people who've studied physics, don't really get it. So let me ask you something. You're sitting there, light is coming through your window right now probably, and you think, well, the light just goes through the glass. Simple, right? Wrong. Completely wrong. Light doesn't just go through glass like water flowing through a pipe. That's not what happens at all. And here's the thing that'll really bake your noodle. Glass is actually opaque. Yeah, you heard me right. Glass is opaque to light. Now you're thinking, I've lost my marbles. You're looking at glass. It's transparent. Obviously, it's transparent. But stay with me here. When a photon, a little particle of light, hits an atom in the glass, that atom absorbs it completely. The photon is gone. The electron in the atom gets excited, jumps to a higher energy level, and that original photon, the one that came from the sun or your lamp, that photon is dead. It doesn't exist anymore. So if every atom is absorbing every photon, how the heck are you seeing through the window? This is the mystery. This is what makes glass weird. And the answer is so beautiful, so typical of how nature actually works, that once you understand it, you'll never look at a window the same way again. What happens is this: the electron that got excited, it doesn't want to stay excited. It's uncomfortable up there in that higher energy state. So it falls back down to its original level. And when it does, it emits a new photon, a brand new photon with the same energy, the same frequency as the one that got absorbed. And here's the crucial part. This happens fast. Really fast. So fast that the delay is basically nothing. But wait, there's more atoms. Billions and billions of atoms. The new photon travels a tiny bit, hits another atom, gets absorbed again, another electron jumps up, falls back down, emits another new photon. This happens over and over and over, billions of times as the light crosses just a few millimeters of glass. Each photon is being destroyed and reborn. Destroyed and reborn. Like some kind of crazy relay race where the runners keep dying and being replaced. Now you might think, okay, that's interesting, but so what? Here's the so what. The direction. When that electron falls back down and emits the new photon, it could emit it in any direction. Up, down, sideways, backwards, any direction at all. If that happened, if each new photon went off in a random direction, the glass would be white. It would scatter light everywhere like fog or milk, but it doesn't. Glass is clear. You see a sharp image through it. So something else is going on, and this is where quantum mechanics comes in and saves the day, or makes everything weirder depending on how you look at it. See, you can't think of one photon going through the glass. You have to think of all the possible paths the light could take. Every single possible path from the light source to your eye. Straight through, bouncing around between atoms, zigzagging like crazy. Every conceivable path. And in quantum mechanics, the photon, or really the probability wave, takes all of them simultaneously. Now here's the magic. Most of those paths, the crazy zigzag ones, they interfere with each other destructively. The quantum mechanical amplitudes cancel out. It's like waves in water. You get a wave going up and a wave going down at the same place. They cancel. You get nothing. Same thing here. All the weird paths cancel each other out. The only paths that don't cancel, the only paths where the amplitudes add up constructively, are the ones that go straight through, or very nearly straight through. So the light appears to travel in straight lines through the glass, not because each photon is actually going straight, but because all the non-straight paths cancel out quantum mechanically. The glass looks transparent because of destructive interference of probability amplitudes. How beautiful is that? Nature's playing this incredible trick, and we just see, oh, light goes through glass, no big deal. But wait, I'm not done yet. There's another piece to this puzzle that makes it even stranger. The speed of light. Everybody knows light travels at the speed of light, right? About 300,000 kilometers per second in vacuum. But in glass, it slows down. Light in glass travels at about 2/3 the speed it travels in empty space. Why? Why does it slow down? And again, the obvious answer is wrong. People think, oh, the light is bumping into atoms, getting delayed, so it takes longer to cross the glass. But that's not it. The photons, the individual particles, are always moving at the speed of light. Always. They can't move at any other speed. That's a fundamental property of photons. They're massless, so they have to move at light speed. Period. So if the photons are always moving at light speed, how does the light slow down? Well, remember what I said. The photons are getting absorbed and re-emitted, absorbed and re-emitted. There's a tiny delay each time an electron absorbs a photon, exists in an excited state, then falls back down and emits a new one. That delay, multiplied by billions of atoms, adds up. The light seems to slow down because of all these little delays at each atom. But even that's not quite the whole story, because if you actually do the calculation, if you work out the quantum mechanics properly, what you find is that the slowing down is really about the phase. The new photons that get emitted, they're not quite in phase with the original wave. There's a phase shift. And when you add up all these little phase shifts from billions of atoms, the net effect is that the wave appears to be moving slower. It's not that anything is actually moving slower, it's that the phase of the wave is retarded, delayed, compared to what it would be in vacuum. This is what we call the refractive index. Glass has a refractive index of about 1.5, which means light travels at 1 divided by 1.5, or about 2/3, the speed of light in vacuum. And this refractive index, this slowing down of the light, is what causes all the fun stuff. Lenses focusing light, prisms splitting white light into colors, mirages on hot roads. All of it comes from light traveling at different speeds in different materials. Now let's talk about why glass is transparent but metals aren't. You can't see through a sheet of aluminum. Why not? Same deal, right? Light hits atoms. Atoms absorb it, re-emit it. So why doesn't it just go through like glass? The difference is in the electrons. In glass, the electrons are tightly bound to their atoms. They're in what we call bound states. When a photon hits, it excites the electron to a higher bound state. Then the electron falls back and re-emits the photon. The photon energy matches very specific transitions between energy levels. For visible light, glass atoms happen to have a gap. The energy of visible light photons is too small to excite electrons to certain higher states, but too big for others. It's in between, so the absorption and re-emission happens cleanly and coherently. But in metals, you've got free electrons, a whole sea of them. They're not bound to individual atoms. They're wandering around loose. When light hits a metal, these free electrons start to oscillate. They accelerate. And when charges accelerate, they radiate. They emit light. But the free electrons can absorb energy at any frequency. And they also collide with atoms, losing energy as heat. The light gets absorbed and turned into heat instead of being re-emitted coherently. So metals are opaque and shiny. The light bounces off rather than going through. And here's another weird thing about glass. It's not actually a solid. I mean, it is, but it isn't. Glass is what we call an amorphous solid. The atoms are frozen in a disordered state, like a liquid, but they're not moving. If you look at a crystal, like quartz, which is also silicon dioxide, just like glass, the atoms are arranged in a perfect repeating pattern, very orderly. But in glass, they're jumbled up, random, like in a liquid. Glass is basically a liquid that's been cooled down so fast that the atoms didn't have time to arrange themselves into a crystal. They got stuck in a disordered configuration. There's this old myth that glass in old windows is thicker at the bottom because the glass flows slowly over centuries. That's not true. Glass doesn't flow at room temperature. But it's not completely false either. Glass is in a metastable state. It's not in the lowest energy configuration. If you gave it enough time, billions of years maybe, or heated it up a bit, it might slowly rearrange into a crystal. But for all practical purposes, at room temperature, it's stuck. It's a frozen liquid. And this amorphous structure, this disorder, it actually helps make glass transparent because there's no regular crystal structure. There's no strong scattering at specific wavelengths. Light doesn't know what to do except keep going forward. In a crystal, you can get complicated interference effects, reflections at specific angles, all kinds of weird stuff. But glass, being disordered, treats all directions more or less the same. The light just plows through. Now let me tell you about something really strange, color. Why is some glass colored? You can make red glass, blue glass, green glass. What's going on there? Well, you add impurities. Tiny amounts of metal ions. Cobalt makes blue glass. Iron makes green. Gold, believe it or not, makes red glass. Ruby red glass has actual gold particles in it. These metal ions have electrons in partially filled orbitals, d orbitals or f orbitals, and these electrons can absorb specific frequencies of light. So white light comes in, the metal ions absorb, say, all the red and green, and only the blue gets through. You see blue glass. But here's the thing, the absorption is real. Those photons actually get absorbed and their energy turns into heat or gets re-emitted as different frequencies. They don't come out the other side. So colored glass is partially opaque. It's blocking some of the light. Clear glass, pure glass without impurities, doesn't absorb visible light at all. or almost not at all. There's always a tiny bit of absorption. Nothing's perfect. But for visible light, glass is pretty much completely transparent, which is amazing when you think about it. This complicated dance of photons being absorbed and re-emitted billions of times, and it all works out so that the light comes through clear as day. But glass isn't transparent to all light. Try shining ultraviolet light through glass. Can't do it. Glass absorbs UV. The photons have too much energy. They excite electrons into states where the energy gets dissipated as heat instead of being re-emitted. That's why you can't get a sunburn through a window. The UV light that causes sunburns gets blocked by the glass. And on the other end, infrared light, far infrared, glass blocks that too. The photons have the right energy to excite vibrations in the glass structure, the atoms jiggling around. Those vibrations absorb the infrared light and turn it into heat. That's why greenhouses work. Visible light comes in through the glass, gets absorbed by the plants and soil, heats them up, they radiate infrared, but the infrared can't get back out through the glass. Heat gets trapped. Greenhouse effect. So glass is only transparent in a specific range of frequencies. Visible light, basically. And that's not an accident. Our eyes evolved to see in the range of frequencies where the sun emits the most light and where water and air and, yes, glass are transparent. It's all connected. Now I want to talk about something that really bothered me when I was learning this stuff. When light hits glass at an angle, some of it reflects. You see your reflection in a window, especially at night when it's dark outside. Why does some light reflect and some go through? And how does the light know how much to reflect? This is a quantum mechanics problem, and it's a beautiful one. Each photon has a certain probability of being reflected and a certain probability of being transmitted. You can't predict what any individual photon will do, but if you send 1 trillion photons, you can predict very accurately what fraction will reflect. For glass at normal incidence, straight on, about 4% reflects and 96% transmits. Where do these numbers come from? They come from the refractive index. The bigger the difference in refractive index between air and glass, the more light reflects. You can calculate it exactly using Fresnel's equations, but the basic idea is this. The light wave in air has a certain phase velocity. When it hits the glass, the phase velocity changes because the refractive index is different. This mismatch creates a reflected wave. The bigger the mismatch, the stronger the reflection. And here's something really cool. If you stack multiple layers of glass with air gaps in between, the reflections from each layer can interfere. If you make the layers just the right thickness, you can get the reflected waves to interfere destructively and almost no light reflects. Or you can make them interfere constructively and you get a mirror. This is how anti-reflection coatings work. This is how dielectric mirrors work. It's all about controlling the interference of light waves reflecting from multiple surfaces. But wait, there's more. Let me tell you about birefringence. Some materials, not ordinary glass but special crystals, have different refractive indices for light polarized in different directions. So if you send light through, it splits into two beams. One beam sees one refractive index, travels at one speed. The other beam sees a different refractive index, travels at a different speed. They separate. This is called birefringence or double refraction. Calcite does this beautifully. You put a calcite crystal on a piece of paper with writing, you see double. Two images. Each image is polarized differently. The light is splitting based on polarization. And this isn't just some curiosity. This is fundamental. It shows that light is a wave with a direction of oscillation. It has polarization. And different materials can treat different polarizations differently. You can make polarizing filters using this. Stack up crystals or use special polymers where the molecules are aligned. These materials absorb light polarized in one direction and transmit light polarized in another direction. Put two polarizers at right angles, no light gets through. Rotate them, light comes through. This is how LCD screens work. Liquid crystals that can rotate the polarization of light controlled by electric fields, combined with polarizers, all based on this weird property of light interacting with materials differently depending on polarization. And let's not forget about dispersion. White light is a mixture of all colors, all frequencies. Red light, blue light, everything in between. And here's the thing, the refractive index of glass isn't the same for all frequencies. Blue light has a slightly higher refractive index than red light, so blue light slows down more. It bends more when entering or leaving the glass. This is why prisms work. White light enters the prism. The different colors bend by different amounts. They separate into a rainbow. Newton figured this out in the 1600s. He showed that white light is composite, made of many colors, and glass can split it apart. Beautiful. And the reason fundamentally is that the electrons in glass respond slightly differently to different frequencies of light. The resonances, the natural vibration frequencies of the electrons are frequency dependent. So the absorption and re-emission process that creates the refractive index is also frequency dependent, hence dispersion. This also means you can't make a perfect lens because different colors focus at different points. This is called chromatic aberration. Red light focuses farther away than blue light. Your image gets blurry, surrounded by colored fringes. Early telescopes and microscopes suffered terribly from this. The solution is to use multiple lenses made of different types of glass with different dispersion properties, arranged so the errors cancel out, achromatic lenses. But it's always a compromise. You can't eliminate chromatic aberration completely, not with regular glass lenses. Now let me blow your mind one more time. I've been talking about photons being absorbed and re-emitted, but you might ask, if a photon gets destroyed and a new photon gets created, is it really the same light? And the answer is, there's no such thing as the same photon. Photons are indistinguishable. You can't tag them. You can't tell one photon from another. They're identical particles. So when I say the light goes through the glass, what I really mean is that the electromagnetic field propagates through the glass. The quantum field. The field absorbs energy from the incoming wave, stores it briefly in excited electron states, then releases it as an outgoing wave. The outgoing wave has the same frequency, the same phase, the same direction as the incoming wave, so we say the light went through. But really, it's the energy and the information that went through. The photons themselves, if you want to think of them as particles, are not the same photons. This is the essence of quantum field theory. Particles are excitations of fields. They're not little billiard balls bouncing around. They're disturbances in fields, and these disturbances can be created and destroyed. What persists is the field itself and the patterns of excitation in the field. And this brings us to the deepest question. What is light? Is it a wave or a particle? And the answer is, it's neither, or it's both. It's something else entirely. It's a quantum object that exhibits wave-like properties in some experiments and particle-like properties in others. When light goes through glass, you need the wave picture to understand interference and phase. But you also need the particle picture to understand absorption and emission by individual atoms. Both pictures are necessary. Neither is complete. Feynman, I spent a lot of my career trying to make sense of this. Quantum electrodynamics, QED, is the theory that describes how light and matter interact. And it works. Boy, does it work. It's the most accurate theory in all of science. We can predict things to 10 decimal places and experiments confirm it. But does it make sense? Does anyone really understand it? I don't think so. We can calculate with it. We can use it. But understanding, in the intuitive sense, I'm not sure that's possible. Glass is a window into this quantum world. Literally, every time you look through a window, you're seeing the result of trillions of quantum mechanical interactions, photons being absorbed and emitted, probability amplitudes interfering, fields propagating. It's all there, happening right in front of you, and you don't even notice. So the next time you look through a window, remember, the light isn't just passing through. It's being destroyed and recreated over and over. It's taking every possible path and interfering with itself. It's slowing down because of phase shifts. It's a miracle of quantum mechanics that you can see anything at all. Glass isn't simple. Glass is weird and wonderful, and a testament to the strangeness of the universe we live in.